Hi, this is Anthony Padone for completeSql. I'd like to start my series called Let's Talk About. I'd like to talk about various DMVs or DMOs or functions, but today we'll talk about memory grants. And we'll be using completeSql to demonstrate various features of what we're talking about and demonstrate. This first instance of completeSql is just running code to create a memory grant, so I'll just minimize that because no concern right now. This instance of completeSql will demonstrate our memory grants. So I'll just bring that up. I'll bring up the session manager, bring up the request, and we'll look at that. So it's running behind the scenes, it's collecting information, and actually these are the memory grants right here, but we'll discuss that after we look at our synopsis. So synopsis in completeSql is always attached to the code that we're running. So we can keep track of our progress, we can learn about what we're talking about, and we can grow with the process. So let's just start a discussion about memory grants. So every session within SQL Server can be within three states as far as memory grants. Either it's waiting for a memory grant, or it's the pending grant, it's consuming a memory grant, so there is an outstanding memory grant that's being used, or it has no memory grant. It's been satisfied by the minimum memory per query, and no grant is required to process. Now, if a memory grant has been granted and it's waiting for a memory grant, these are the key columns to refer to in memory grant DMV. The QID is the ID of the queue that's housing the request that's waiting for a memory grant. The wait order, that's the order of the item within the queue. The wait time in milliseconds, how long has it been waiting in the queue, and the grant time. The grant time is equals null, means that the grant was not granted yet. So those are just items to show that the memory grant has been granted, but it's waiting for that memory grant in a queue. Now, a quick definition of memory grants: it's the extra memory needed for sorting and hashing, and this extra memory is not required, but is used to speed up processing. The grant reserves memory before execution, and this helps to improve reliability. Reliability of the system, reliability of the flow of the processing. And as always, memory is stolen, and actually the buffer pools, the buffer frames are stolen from the buffer pool and given to the memory grants, okay, on demand. And this can cause memory pressure. In our case, it probably causes internal memory pressure. Now let's review the life of a query. A user or a process or a session presents a query. The query is compiled, it actually resolves the logical or physical. It's stored in cache as a cached plan, and then there's execution of that cache plan. The cache plan, as we know, is reentrant, so one plan can satisfy many requests, and each request has its own user execution context that stores individual variables that it needs for processing. Now, as far as memory, there's basically four large consumers of memory in SQL Server. The first one, as we mentioned before, is a buffer pool. Buffer pool houses the buffer pages from the data pages and index pages. Also, the compile process, which is a short-term store, but it steals memory from the buffer pool to process various candidate plans of the query that will be used for the execution of the query. So it's a short-term, but it needs a lot of memory for that. The cache store is a long-term process that'll store the cache plan, store the compiled plan, and hopefully it's there for reuse, so it can be reused and not go through the compile process. Okay. Also, we need memory for execution. So the execution requires a certain amount of memory, and it may need extra memory for the sorting and hashing that it requires to speed up the processing. If the memory is not there, it may have to go to disk, and disk, of course, can be very, very slow from the thrashing back and forth, and then this is short-term memory. Along with that process, we have a memory broker. The memory broker is tightly coupled with the buffer pool, and its job is to brokerage memory across those four consumers, which is the buffer pool, the compile process, the cache store, and the execution. So he brokers memory to keep down the internal memory pressure of SQL Server, and also to hopefully to avoid external memory pressure from the Windows process. Okay. Another concern as far as processing and memory grants would be the DOP, the degree of parallelism. If we have multiple threads processing and we're using memory grants, those threads also need memory for sorting and hashing, and that can increase our demand for memory. Let's talk about the flow of a request within SQL Server. It first must decide whether to use DOP, degree of parallelism, whether it's many threads or zero threads. So that can be a concern to us because the more threads, it could use more memory for the sorting and hashing and deplete our memory and cause some internal pressure. Of course, memory grants, will it have enough memory for memory grants? The memory for sorting and hashing. And what the process tries to calculate the ideal memory required for the execution of the query. The ideal memory is basically what it can store in memory as far as the DOP, the degree of parallelism, and the additional memory needed for the sorting and hashing outside, as I have it here, the per query limit. There's always a set determined amount that the query always has to begin with, but the extra memory is through the memory grant. Also, the memory grants are handled by a resource semaphore. Now, semaphore, as I have listed here, is a non-exclusive lock that limits concurrency. So it's not a yes or no type of lock. It allows multiple processes to process with a predetermined limit of how many it will process. Let me just read my definition. It's a construct used for controlling access by multiple processes to a common resource in a multi-user environment. So let's just say that I have a resource semaphore, or semaphore, so to speak, that has a limit or a processing limit of 7. So therefore, it would allow 7 processes to process all at once. And when one leaves that process of processing, another will enter and just keep it to a count of 7. So it'll allow more processes to process, but with a cap on that. Okay, now SQL Server, as far as memory grants, has 5 queues for processing. And each one is based on the query cost. So depending on the cost of the query, it will be placed in one of those 5 memory grants for processing. And this is for the fairness of processing. For instance, a smaller query that has a smaller request of processing, a less demand on the system, will go to a smaller queue where it can process much quickly, as opposed to waiting behind a larger processing query with a larger processing count. So there's 5 queues for processing. Within SQL Server, there's multiple ways of tracking memory grants and semaphores, resource semaphores that were utilized. Our discussion will be using the DMVs, which is the memory grant DMV, in real time. So we can capture information in real time from the DMV and review that. It's very important to track memory grants because even though they can speed up processing by using memory, of course, everything's internal to the memory, it can also slow down processing because the throughput can be reduced because of the waits for memory and stealing the memory from the buffer pool and stealing it from the other consumers of memory, and that can slow down process. So it has to have a fine balance between memory grants and the memory utilized for execution of our queries. We can look at the storage. We can look at the wait stats and look for a resource semaphore wait, a wait time of the resource semaphore. This can show us that there were waits for the resource semaphore. Another way of looking is a better way also is looking at the query plans. You look at the query plans, you look for memory fractions. And this shows us that after the execution of the query, that memory was granted for sorting and hashing, and you can see how much it was granted. But this, of course, this is after the execution. That's one way of doing it, but I truly prefer the real-time processing of memory grants within completeSql. And you can collect that information live and then respond to it quickly. So as you can see, this is our synopsis of memory grants. And all the queries, all the DMVs actually in completeSql come with synopsises, and you should add to that and correct it and grow with that. We never want to backtrack as far as our learning. We just want to add to what we know and grow. So if you're short on the memory as far as what memory grants stand for, review yourself, look at the synopsis, and then proceed from there. So we'll get into the actual memory grants being collected. This is running right now. We collected a lot of memory grants, and let's review that what we collected. So we'll look at the request time of the memory grant and the granted time. They're the same, so therefore there was no wait for the memory grant. But since we're in this display here from the memory grants, we were granted a memory grant. The wait time again shows that there was no wait for the memory grant, but we do have a memory grant since we're here. This is the requested memory, the ideal memory that we wanted. We wanted this amount of memory to process to put everything in memory, our sorting and hashing, and we requested that, and we were granted that. So the systems decided that we had enough memory to process, and it was given to us. But as you can see, as mentioned before about the required, I'm only required to have 512. So if I had 512 memory, that's enough to process my request. But we know that would be very, very slow. We know that the processing would be through disk, or there'd be a lot of waiting for the extra memory that it needed, and it would slow down throughput through the system. This keeps track of how much memory it's accumulating during the processing, because it builds up the memory it needs. This is the cost of the query, 149. So it's a high processing, high cost query, and I'm sure it was processed in one of the higher end queues, where the higher end processing happens for the larger queries that have higher requests. Yeah, as you can see here, it's 0 is small, so it did not come from a smaller queue, but from a larger queue. The queue ID is null, so it was granted the memory, but it was not waiting for the memory, so there's no ID. The wait order, there's no order because it didn't wait for the memory. As we saw, it was granted immediately. And we have the query here. So we'll look at that in a second. And this is the query that was running. This is causing the request for the memory grant. And as you can see, it's just one large query, selecting top X amount, all the columns, no indexing, and order by. So the system decided that it needed a memory grant, it needed memory for the sorting, and it was provided for us. So as you can see, we collected information in a live process using memory grants, and it's at our fingertips here. We can decide, we know the query, we know how much is required, and you can track this against other requests, and you may start to limit the degree of parallelism. You may start to limit how much memory, maybe through the resource governor, so you have possibly more throughput for your system. So memory grants is something you should always watch out for. You should obviously track, and you should monitor, and particularly through completeSql. Also, as through completeSql, always keep your synopsis. Always write information about what you're processing, so it's at your fingertips, and you can grow with the whole consumption of your learning about DMVs, DMOs, and functions. So that concludes our discussion about memory grants. I hope you learned something from that. And completeSql is an excellent way of growing, learning, and processing and exploring the internals of SQL Server. I thank you for listening, and stay tuned for my next course and discussion about Let's Talk About. Thank you very much. Bye-bye now.